Hello friends, welcome to this lecture on computer-aided power system analysis. We have been looking at the structure of the Jacobian matrix. So, let us look at that now with a more detail. So, now just to take a simple example, this is just to show that what would be the structure. Suppose I do have a bus, I do have a system, just a 4 bus system. So, these blue lines are buses. So, this is bus 1, bus 2, bus 3. So, these are all lines. So, this is bus 1, 2, 3, 4. So, n is equal to 4. So, n is equal to, so the number of states 2 into 4 minus 1, that is 7. So, then what is the state vector? State vectors would be nothing but V1, V2, V3, V4, theta 2, theta 3, theta 4. We generally prefer to write the theta before and then after this V, just to it is just a matter of notation. Just so we usually like to write like this, theta usually. So, this is 7 cross 1 vector. Now, suppose my measured quantities are P12, let us say P21, let us say Q14, let us say QP41, let us say Q34, let us say P43, 1, 2, 3, 4, 5, 6, let us say P2, let us say Q3, and we also measure, let us say here in this I 2, 3 magnitude. So, my measured quantities are Z are P12, P21, Q14, P41, P43, Q34, then I23, P2, Q3. So, say that these are my measured. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, I have got 9 measurements, 7 states. Please note that because of the losses P12 is not equal to minus P21 because of loss. So, because of loss. So, now what would this Jacobian matrix would look like? So, then therefore, for the Jacobian matrix would be essentially. So, then here we say that this is Z1, this is Z2 and dot dot dot, this is Z9 and this is X1, this is X2 dot dot dot, this is X7. So, then therefore, the Jacobian matrix would be H would be, for example, del P1 del P12 by del theta 2. So, del P12 by del theta 2, then del P12 by del theta 3 dot 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 del P12 by del V4. Similarly, the second one would be del P21 by del theta 2, del P21 by del theta 3 dot 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 del P21 by del V4. and up to this we will go, and the last one is del q3. So, del q3 by del theta 2, del q3 by del theta 3, and dot 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 del q3 by del p 4. This would be the Jacobian matrix, right. So, the first row would be corresponding to P12. So, first row is P12, second row is P21, and similarly this is the ninth row is Q3, this is the ninth row, right. So, this is the first row, this is the second row, and similarly the first column is theta 2, this is the first column theta 2, second column theta 3, and so on and so forth. Now, we have already seen, now we know that P12 is a function of only V1, theta 1 is 0. So, then therefore, theta 1 is not an unknown quantity. So, it will be V1, V2 and theta 2. P21 is also another function of also only V1, V2, theta 2. So, then therefore, what? So, then therefore, I mean which quantities would be only basically non-zero. So, essentially here, so then essentially here del P12 by del theta 3 is equal to del P12 by del theta 4 is equal to del P12 by del V3 is equal to del P12 by del V4 would be all equal to 0. Only non-zero partial derivatives would be only corresponding to del P12 by del V1, del P12 del V2 and del P12 del theta 2. All the other quantities would be 0, right. Similarly, also for del P21, so then therefore, we can write down. So, then here if I, so then here I can write down the H matrix is something like this. So, then H matrix. So, first one is del P12 by del theta. So, this is non-zero, then this is 0, this is 0, then also this is non-zero, non-zero, this is non-zero, this is non-zero, this is 0, this is 0. We note that, we just note that here, let us say this column is corresponding to theta 2, this is theta 3, this is theta 4, this is V1, this is V2, this is V3, this is V4, right. And this is corresponding to P12. Similarly, for P21 also it would be V1, V2 and theta 2. So, for P21 also it would be this 0, 0, 0, 0, this is non-zero, this is non-zero, this is 0, this is 0. So, this would be P21. Next is Q14. Now, we know that Q14 is a function of some function of only V1, theta 1 is 0, it is only V1, V4, theta 4. So, Q14, so Q14 so Q14 would be V1. So, this is a non-zero. So, V1, so V1, then V4, then theta 4 all are 0. Then we have, let us write P41, P43, P41 also, P41, then P43, then we have Q34 I23, then it is Q34, then it is magnitude I23, then it is P2Q3, then it is P2, last is Q3. Okay. P41 also would be the function of V1, V4, theta 4. So, it would be also V1, V4 and theta 4. So, this 0, 0, 0. P43 would be a function of, let us say, some function g, it would be theta 3, theta 4, V3, V4, that we have already seen. So, P43 would be theta 3, theta 4, V3, V4, V3, V4 all as 0. Q34 also would be something like this, 0, 0, this. So, this is Q34, and I23 would be again a sum function G2, say this is G1, it would be theta 2, theta 3, V2, V3. So, V2, so theta 2, theta 3, V2, V3 and all would be 0. P2, now P2 is a function of, now P2 is actually j is equal to 1 to 4 V2 Vj Y2j cos theta 2 minus theta j minus alpha 2j. Now, here if we look at the structure of this, so then therefore, in the Y bus matrix which quantities would be 0? I mean, there is no direct connection between bus 2 and bus 2 and bus 4, and also there is no direct connection between. So, now when we are looking at P2, so then therefore, there is only direct connection between from bus 2 is bus 1 and bus 3. So, there is no direct connection between bus 2 and bus 4. So, then therefore, P2 would not be a function of, P2 would not be a function of, P2 would be only a function of, P2 would be only function of V1, V2, V3, theta 2 and theta 3, because it would not be a function of V4 and theta 4 because of the simple reason that Y24 would be 0 as Y24 is equal to 0, as Y24 is equal to 0. So, P2 would be simply a function of V1, V2, V3, theta 2 and theta 3. So, P2 would be theta 2, theta 3 and V1, V2, V3, 0, 0. And last but not the least, Q3 is, again we write it here, k is equal to 1 to 4 V3 Vk Y3k sin theta 3 minus theta k minus alpha 3k. Now, if we look at the structure, bus 3 is only directly connected to bus 2 and bus 4. So, then therefore, bus 3 Q3 would not be a function of V1 and theta 1 is already 0. So, then therefore, it would be V2, V3, V4, theta 2, theta 3, theta 4. So, then it would be V2, V3, V4 and so that is how it would look like. So, then you see, so then therefore, depending upon the So then here in this case we have looked into all kind of measurements, and we can see that depending upon the type of measurement and the interconnectivity, depending upon the type of measurement and interconnectivity, there would be also, I mean, this particular Jacobian matrix would not be also a full matrix, it will also have many zero elements. Here in this case we have taken a very simple example, only a 4 bus system, but if we take a large system, so then therefore this matrix also would be a sparse matrix. So then therefore we can also apply here these sparsity techniques what we have already discussed earlier. But then this particular simple example gives us the structure that depending upon the type of measurement, that how this particular Jacobian elements would be computed. So obviously, I mean, which are already 0 0. So then therefore only this non-zero elements would have to be computed at each and every iteration. So this is just a theoretical example, but now let us look at numerical example. So for numerical example, so let us look at simple 5 bus system, and this simple 5 bus system we have already taken earlier when we were discussing about the load flow analysis. Now in this system, this is the load flow result. So now in this system, this is the load flow result. Please do remember that in this system bus 1 is the slack bus and bus 2 and bus 3 are 2 generator bus, and both of them have got voltage specified as 1.0, and then bus 4 and bus 5 are PQ load, and those same data and etc. whatever we have discussed in the case of load flow analysis are also utilized here. So then this load flow analysis is this. Here of course we have not taken any, we have not taken the case of generator limit violation. So then therefore all these voltage magnitudes are maintained equal to 1. So this is the load flow result. Now if I do state estimation without any error, now what we have done, that after this load flow result we have calculated that what are the power flow through all the lines, what are the power flow through all the lines in this line, in this line. So in all these lines what are the power flow we have calculated by utilizing these values. These power flow results we treat as the ideal value of the measurements. These power flow results we treat as the ideal value of the measurements, which are true values, absolutely ideal and true values. Now here of course, now because it is a 5 bus system, so then therefore the total number of states is 9. I mean, except this angle at this bus, all the other bus voltage and magnitudes are to be estimated. So then therefore total number of state variable is 9. And then when we do this state estimation with these 12 measurements, P12 denotes the real power measured between bus, I mean measured on the line bus 1 2 measured at bus 1. So then here also Q12 denotes that the reactive power flow over line 1 2 measured at bus 1. Similarly P15 is real power flowing at over the line bus 1 5 measured at bus 1. So then therefore when we are talking about Pij is nothing but the real power flow measured, I mean it is basically the real power flow over line Ij measured at bus I. So if we take these 12 ideal measurements computed from these results and then we back calculate all these voltage magnitudes and angles, we get the identical result, almost identical result. So then therefore we can see that when we take the ideal measurement, that is the true value of the measurement, state estimation result gives the exactly this load flow result. Now suppose now we are taking error in the measurement. Suppose we now taking error and we take that all these meters have gotten sigma of 0.02. So that means we are taking all the measurements to be of equal weightage. So we are taking all the measurements to be equal weightage. So then So, when I take this error and utilize the same 12 measurements, now we get different values. Now we get completely different values. Earlier these 3 was maintained at 1, earlier these 3 was maintained at 1, but now these values have now completely changed. These values are now completely changed. So, then you see that whenever there is an error, so then these estimated values are not equal to the true values. So, we can say that these values are the true value, but the using those erroneous meters or rather erroneous measurements, when you do this state estimation result, the basically this state estimation results do not give the true measurements, or rather do not give the actual value of the states. Now, suppose we do increase the number of measurement, that we still take sigma is equal to 0.02, and if we do increase the number of measurements, then we get much better result, then we get a little better result. And why we get this little better result? Because more number of meters, and if these meters they do not have bad data in them, so then therefore more number of meters and more number of measurements will actually improve the estimated states, will actually improve the estimated states. So, then when you see that when you take 18 measurements, and these 18 measurements are nothing but all of these 12 measurements said earlier plus these 6 measurements. Here for the sake of simplicity, we have only taken P and Q flow measurement over all the lines. Similarly, with the same sigma, when we keep on increasing, again these values have also little improved, but then that improvement is not much, but then still they are improved, and my 24 measurements are nothing but like this. So, then all of this 18 plus this. Now, these results are due to the now these results correspond to the fact that there are no bad data. Now, look at that if there are bad data. Now, here we have taken alpha is equal to 0.05. Now, if I take m is equal to 24, so that is this. So, then therefore, if my m is equal to 24 and my total number of states to be estimated is 9. So, then therefore, my k, that is the basically the degree of freedom is 15. So, k is 15 and alpha is equal to 0.05. So, if we look at this particular table of chi-square distribution, we find that C k alpha is equal to 24.9958. And then utilizing these estimated values, if we now calculate this z hat vector, and then from that we can calculate f hat value. So, then this f hat value comes out to be 1.4789. See that this estimate. So, that this estimated value of the objective function is much less than this. So, then therefore, we conclude that there is no bad data here. Now, suppose in this analysis, in this case, if we calculate the value of with these true values, if we calculate the value of real power flow over line 4-5 measured at bus 5, and if we calculate that particular value of P54, P54 is nothing but the real power flow over line 4-5 measured at bus 5. If we calculate that value, the true value comes out to be 0.2193. But now we assume that suppose this particular meter has gone bad. So, instead of measuring somewhere closer to 0.2193, that is, I mean, even if this meter has gotten sigma, basically error sigma is equal to 0.02. So, its measured value would not be very far away from this value. Its value would not be equal to this, but that particular measured value would be quite close to this value. But now suppose that this meter has gone completely bad and this error is too much. So, now suppose that this instead of measuring any value closer to this, it is now actually measuring a value 10.2193. So, it is almost 50 times. So, it has gone completely bad. So, now with this bad measurement, with this single bad measurement, if we now calculate, if we now do this state estimation, then we find that my FAD value is 196,532.65, which is much more than this, much more than this. So, then therefore, we conclude that there is certainly a bad data. So, when we conclude that there is certainly a bad data, then we calculate for each of these 24 measurements, then we calculate R dash matrix, and then subsequently we calculate the quantity EI dash by RII dash. And so, then therefore, we get the 24 values of EI dash by RII dash, then I take their absolute value and I take their maximum value, and I find out that what is the index of that maximum value. I find that the index of that maximum value is exactly given by this. So, that then basically the index of the maximum, so then this index of the maximum value is, it is indicating that this particular measurement is bad. So, when therefore, in this example, for example, if I say that it is P54, for example, this one, so then it was giving the index as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, then after that what you do, once we identify, so then therefore, this particular measurement has got the maximum value of EI dash by RRI dash. So, then we remove it. So, now my effective number of measured values becomes 23. So, now my effective number of measurements become 23, and I still keep this alpha is equal to 0.05, and with this I again find out that what is the value of Ck alpha. Now, please note that now k becomes 14, because my number of state is 9 and my total number of measurement is 23. So, now my k, that is the degree of freedom, becomes 23 minus 9, that is 14. So, then with this 14 Ck alpha, so then with this 14.05 I get this value, and when I do this my state estimation with this 23 remaining measurements, I find that my FAD value is 1.4721. So, again we now conclude that there is no bad data in this system. So, then therefore, whatever is the estimated value, those are the acceptable estimates. So, this is the basic procedure. Now, here one question comes into mind. So, you can see that to cater for the presence of this bad data, we have to make that our measurement value, we have to maintain that our number of measurements should be more than the number of states. Now, in case, now if we are able to put meters everywhere and bring those values to our control center, so then in that case we will be getting those measurement values. But if not, so then we have to have some other way of taking this or rather basically some other way of generating these measurement values, right, and these are called the concept of the pseudo measurements as well as the virtual measurements. So, these concepts we will continue in the next lecture. Thank you.